Question number 65. The plates of a capacitor with the given capacity 10 microfarad is charged to 60 microcoulomb, and then this is joined together by a wire of resistance 10 ohm at t equal to 0. What happens when you charge it with a resistance, connect it with a resistance after charging it, and essentially you are shorting it or starting a discharge process on the capacitor. Then the charge on it starts going down, and we need to find the charge on this capacitor at t equal to 0, 30 microsecond, 120 microsecond and 1 millisecond. So I have a lecture on charging of a capacitor and discharging on a capacitor. I would request you to go through it and check its detail once you have gone through this chapter. I have explained it very clearly, and I have derived the formula on it but basically this is the capacitor which is charged to some voltage or some charge on it, and when you connect it to this resistor, let's say you suddenly put this switch down, then this charge starts flowing through this, completing this circuit, and then the charge on this capacitor starts going down, and this is the curve that shows the amount of the charge on this capacitor with respect to time. So Q is a function of t, it's varying with t. Initially it's at Q is equal to Q naught, and gradually it's going down at after a long time it tends to 0. And the charge on this capacitor is given by Q is equal to Q naught e to the power of minus t divided by RC. You can check the accuracy of this formula by putting t is equal to 0. At t equal to 0, this becomes e to the power whole thing 0, and Q becomes equal to Q0. When t is equal to infinite, this becomes 1 upon e to the power of infinite, and 1 upon e to the power infinite is 1 upon infinity or 0, so Q becomes 0. So our formula looks like good. So we can proceed with it, trying to find at t is equal to 0, that is the first question. We have Q is equal to Q naught, and we are given it as 60 microcoulomb. Now at t equal to 30 microsecond, it becomes Q is equal to 60. Q naught we know is 60 microcoulomb multiplied by e to the power of minus t. T we need to find out at 30. Let me see, 30 microsecond here. 30 into 10 to the power minus 6. You converted micro to 10 to the power minus 6 divided by RC. R is 10 and C is 10 microfarad. So 10 into 10 to the power minus 6, 10 to the power minus 6, 10 to the power minus 6 go away. It becomes 0, 0 goes away. E to the power of 60 microcoulomb into 10 to the power of e to the power of minus 0.3. Now how do you calculate e to the power minus 0.3? We know that e to the power x is 1 plus x square by factorial 2 plus x cube by factorial 3, so on and so forth. So e to the power minus 0.3 will be 1 minus 0.3 plus, because x is minus 0.3, plus x is 0.3, x square is 0.09 by 2, plus so on and so forth. We will not calculate it because as the term progresses, this square goes lower and lower and they can be neglected. So it becomes equal to 1 minus 0.3 is 0.7 plus this is 0.045 up to 2 significant digits is roughly equal to 0.74. So 60 multiplied by 0.74, it becomes 6 into 4, 4, 2, 6 into 7, 42 plus 2, 44.4 microcoulomb. Now we have on the C, when t is equal to, I want to go through the process of mathematical calculation as well, because in exam you are required to pay attention to the detail and you should be able to reproduce the results, final results accurately to get the full marks. So at t is equal to 120 microseconds, we have Q equal to 60 e to the power of 120 microsecond is 120 10 to the power minus 6 divided by 10 ohm multiplied by 10 microfarad. This much of microcoulomb because we have taken 60 and 10 to the power minus 6 out from here. So 10 to the power minus 6, 10 to the power minus 6 cancels. This becomes 60 e to the power of minus 1.2. And again using the same thing that we did for e to the power, we can apply the same thing here as well. It's 60 into 0.3. How do we calculate? 1 plus nx plus n into 1 plus x square by factorial 2. 1 plus x is minus 1.2 x square becomes 1.44 divided by 2, or this becomes 0.72. And then you can, but probably that is one way, but the problem with this, you will have to take a large number of terms, and this keeps on increasing, so this thing does not work. What we have to do is, we have to split it into two parts, e to the power minus 1 and e to the power of minus 0.2. So this becomes e to the power minus 2 is 1 plus nx plus plus x square by factorial 2. So nx is 1 plus x is minus 0.2, x square by factorial 2 is 0.04 by 2. So this becomes 1 minus 0.2 is 0.8 plus 0.02 is 0.82. And 0.82 and multiplied by e to the power minus 1, e to the power minus 1 is 2.7. So 0.82 we can write 0.81 so that it's easy to divide it by 27. So 3, 9 times 27, 3 into 27 times 81, and 9 divides this, so this becomes equal to 0.3. And then we can multiply this by 0.3, it becomes 18 microcoulomb. So something like that, you have to keep these things, because you are not allowed calculator in the exam, so you need to do these things. In problem number D, we need to find t at 1 millisecond, so we'll have q is equal to q naught e to the power of minus, t is 1 millisecond, so it's 10 to the power minus 3 divided by r is 10 microfarad. So 10 to the power minus 3, 10 to the power minus 3 cancels, becomes 10 to the power 3 here when it goes up, and this becomes 10 to the power 3 cancels with this, we have e to the power of minus 10. Now how do we calculate e to the power minus 10? E to the power of 10 means e is 2.7, so we need to essentially calculate 2.7 into 10. So basically, sometimes you need to just simply multiply it, 2.7 multiplied by 10, and you should be able to get pretty close answer. But this is a very big number, so q tends to 0 after a long time. That is what we want to understand about the capacitor behavior.